Well, good afternoon, everyone. Thank you for joining us. We are from the Salesforce Monitoring Cloud Group, and today we are going to share insights from operating large-scale Flink streaming jobs, which process 300 billion telemetry events every single day. My name is Amrit Sarkar. I'm a lead engineer in the Monitoring Cloud Group at Salesforce. I have over 10 years of experience in software engineering, specializing in big data and search in Kubernetes, focused on MLOps and observability use cases. Over the past 4 years, I have dedicated my efforts in streaming technologies and currently building and scaling tracing capabilities for the internal Salesforce services. I have my colleague Vineet with me, who will take us through the first half of the presentation.
Awesome. Thanks, Amrit. Hey everybody, my name is Vineet. I have over 2 years of experience in monitoring and observability space. I enjoy building tools that help improve visibility in complex cloud environments. Today I'll talk about the service dependency tool which we have built using Flink. So let's get started. Real quick, what do we have on agenda? I'll talk about what distributed tracing is and the service dependency graph feature. This followed by the data challenges we had which led us to build the Flink platform. Then we'll talk about our Flink job setup and the architectural choices. Post that, we'll talk about the learnings we have had from building this pipeline, and we'll end the session with what we have on the future roadmap. Let's get started. So what is distributed tracing? As we all know in today's microservices world, when a user request comes in, it doesn't stay within one service. It flows through dozens of microservices, such as authentication system, payment system, recommendations, and more. So when this request flows through these services which have tracing enabled, similar to logs and metrics, they also emit a tracing telemetry signal, which we call a span. Now, think of span as a single unit of work. It could be a database call, RPC call, or a call from one method to another method. And every span has a span ID, trace ID, and metadata associated with it. This metadata could be start time, end time, or the operation performed, and much more. Now, when we take a collection of spans which have the same trace ID, what we get is a trace. And this represents the whole user journey from start to end. So an important property of distributed tracing is spans carry parent-child relationship. We not only see what has happened, but also the order in which the request has happened. So this is the foundation that lets us build service dependency graphs. Here we have an example of a single trace flowing through our system. The request starts from the top and it ends at the bottom. So the different unique colors which you see on the left each indicate a service, and the horizontal bars you see on the right indicate the time taken by each operation. And this is one single trace. So when we take hundreds and millions of such traces and try to correlate them together, what we get is a complex view of our microservices world interacting with each other. So we use that to create the service dependency graph. And this is what you see here on the left. So at Salesforce scale, we have hundreds of microservices calling each other in intricate patterns. This graph gets more complex and messier. And we often refer to this as a hairball view of our ecosystem. And this is the reality of the modern distributed systems. But if we take a pause and take a closer look at this from a transactional view, what we get is a transactional service dependency graph. And this is what we set out to build using our Flink pipeline. Now, the goal is clear. Like, how do we take these individual spans, build traces out of it, and analyze them for service dependency edges? For this, we had to consider the following data challenges. First is we deal with highly variable trace size. We have seen trace with spans ranging from 10 to 300K. Now, this is a pretty unpredictable distribution pattern. And we needed a system where we could dynamically configure resource allocation and also have state management. Next is dealing with Kafka spike. So we ingest from a multi-tenant Kafka cluster where the traffic is driven by our tenants. And our solution needed it to take into account the management of uncontrollable volume and also unpredictable traffic spikes. Third is out-of-order events. So this is a problem we need to consider in any real-time processing system. And since a trace flows through multiple services, the spans may arrive out of order due to various reasons. And finally, to make things more interesting, the trace volume data at Salesforce is growing at approximately 30% annually. So we were looking for a system that could handle extreme scale in real time and also provide us with the ability to correlate spans into traces and then convert them into service dependency edges. And that brings us to Flink. This is where it shines. Its core architecture helped us solve all these challenges. Firstly, it supports stateful operations. And this was needed for us to reconstruct the whole trace from individual spans. Secondly, its real-time processing capabilities. So it has the ability to process at massive throughput with low latency, and it is also critical for us to build a real-time troubleshooting tool. Third is event time semantics. Now, this is useful to handle the out-of-order span scenario. And finally, Flink's rich APIs. So these API provided us with the ability to implement custom operators. So Flink was the engine that made large-scale service dependency pipeline possible at Salesforce in a very short period of time. With all that said, here's a high-level view of our Flink pipeline, which makes service dependency possible. We start from the top left. We have an Amazon SQS source connector, and this consumes SNS events. These events are generated when the data is returned to a global S3 bucket from our Kafka partitions. Now, once the data is written, we have the entire Flink job on the right. We have various operators in the Flink job. It starts with the source operator. This operator downloads and deserializes the span data from S3. And post this, the other operators perform filtering and correlation of spans to build the edges. So the output of our pipeline is we start with spans and we end with service dependency edges. We'll take a closer look at this pipeline in the coming slides. But once the service dependency edges are generated, we write the data to a Kafka sink from where it is written to Druid. We use Druid for our long-term storage and also for its ability to perform quick analytical queries. And our API layer is built directly on top of this, and this is what powers the UI. So this whole pipeline makes this service dependency graph possible. This is a screenshot from our UI, and this graph serves as a critical tool for our engineers during an incident. So each node here represents a unique service, and directed edge represents a call from one service to another service. The edges in this graph are also enriched with information such as number of requests, min latency, max latency, error count, and much more. So as you can see, some of the edges are red in color. This indicates that there's high number of errors identified for calls between these services. So whenever a service begins to show increased latency or errors, the service owning team can use this tool to immediately see the performance of all the services it depends on. And they can identify the root cause. They can also see all the other services that are dependent on them. This helps determine the blast radius. So this real-time map of our entire ecosystem helps debug issues in seconds or minutes instead of hours. Now let's go deeper into the Flink job layout. We have 5 main stages for which we have operators. Stage 1 and 2 is ingestion and filtering. Stage 3 is trace building. Stage 4 is edge building, and stage 5 is edge aggregation. So we start with raw telemetry stream of spans, and we key this by trace ID at the source operator. What this guarantees is that all the spans end up on the same task manager, which we need for trace reconstruction. And next, once these key spans are passed through the filter, we pass it through the filter operator. At this stage, we have various filtering strategies. I'll talk about 2 of the main filtering strategies. One is time-based filtering, and second is service-based adaptive filtering. In time-based filtering, we filter out any spans which are older than 2 days. And in service-based filtering, we sample out spans from services that generate a large amount of trace data of the same trace data. So post this filtering, 30% of our data is reduced. And we sample out 30% of our data is reduced while we maintain the data fidelity. Next, we have the trace building operator. Now this is where most of the heavy lifting occurs. Here we reconstruct the whole trace using the spans. At this operator, we maintain a 3-minute context window to handle out-of-order spans. Here we also have a count trigger to cap the maximum number of spans in a window at 3000. This is to ensure that there's no memory overflow issue due to unusually massive traces. And then we have the edge building operator. Now this operator analyzes the parent-child relationship within the trace to determine the service-to-service calls. These calls would become edges on our service dependency graph. At this stage, we enrich each SD edge with 40 plus attributes. The attributes would be details about the source and destination service, the operation performed, the topology information, and much more. Once the service dependency edges are built, we have an important operator, which is the edge aggregation operator. Now, the edges generated at the previous operator are rekeyed and passed through this operator using their composite key. So, and we have a 1-minute tumbling window over here. This year, we aggregate the edges and compute metrics such as the duration, error count, latency, and much more. The importance of this operator is the cardinality is reduced massively. And this is the key for us to enable faster query performance for our users that interact with the tool. So overall, we start this pipeline with approximately 200 million spans per minute, and we end up with 400K service dependency edges per minute. And that's 99.8% reduction in data. So here we have a snapshot of our Flink job running in production. It has all the operators which I just spoke about. Notice how the parallelism changes here between each operator. We'll take a deeper look at this. So for the ingestion stage, we have a low parallelism of 15. Here the operator consumes spans from S3 bucket. So after thorough testing, we concluded that limited connections would prove optimal for the upstream server. Hence, we configured the parallelism low here. And next, at the filter and trace building stage, we have the parallelism of approximately 1100. This is where stateful operations happen for the trace reconstruction. Hence, the parallelism is increased. Here, each task manager manages construction of approximately 20 parallel traces. Post that, we have the edge building stage. Now here the parallelism is approximately 2000, and this is where most of the heaviest computation occurs. The whole trace is analyzed, the service dependency edges are determined from here. Therefore, this has the highest parallelism. And finally, the edge aggregation stage. Here again, we have a high parallelism of 1400. This is because most of the data is reduced at this stage, but we still need memory to aggregate the edges. And also here, the key stream is changed from trace ID to service dependency edge. We also have a sync operator in the end where we maintain the same parallelism because Kafka partitions can handle multiple connections efficiently. So we arrived at this configuration based on two key learnings. First is we chain operators with matching parallelism wherever possible to avoid data shuffling. Second is we ensure that each operator's parallelism is direct multiple of the number of task managers. Now this is to guarantee that there's equal workload distribution across the worker nodes. Next, we focused on minimizing network shuffling in our job. So for our use case, as I mentioned, we needed to reconstruct the trace in real time. This meant the input data stream had to be keyed by trace ID. Now, initially our data stream was messy. Spans belonging to the same trace were on different partitions. So you can see the consequence of this in the before diagram. Different task managers consume from different Kafka partitions. And since the spans were on different partitions, during runtime, Flink was forced to perform expensive network shuffling operations for the spans to reach the right task managers. This process was consuming a lot of network bandwidth and CPU cycles. And the result of this was a very unstable and high latency pipeline. We solved this problem by working closely with our collector team. We ensured that the data is co-located at the source. And this way we ensure that all the spans from the same trace are on the same task manager to begin with. The result of this is we saw 98% reduction in span movement between the task managers. This eliminated the massive network shuffling operations we saw on Flink earlier. And this change significantly improved our pipelines and made it more stable and decreased its latency. So we could now process more with the same number of resources. Next is multi-cluster setup. So building on our previous optimization, we also unlocked the ability to scale horizontally. Since it is now guaranteed that all the spans from a trace will be on the same partition, we can now configure multiple Flink jobs to consume from disjoint set of partitions. For example, let's take a look at this diagram. We have job 1 and job 2. Job 1 consumes from even numbered partitions and job 2 from odd numbered partitions. And this provides us with two huge operational benefits. One is linear scaling. To handle our 30% volume growth, we don't have to grow one monolithic cluster. We can now simply provision new Flink clusters and rebalance a set of Kafka partitions to it. This makes scaling predictable and repeatable. And second and most important factor in a multi-tenant environment is failure isolation. Let's say we have unpredictable traffic spike on one of the partitions driven by tenant, and this partition is job 1 is configured to consume from this partition. This would not affect job 2, and this will make sure that at any given point of time we have some data to work with in real time. So this change helped us transform our pipeline from struggling with back pressure to running smoothly at scale. With all this said, I'll hand it over to Amrit, who will talk about the other interesting things we have done.
Yeah, thank you, Vineet. While adopting Flink as a streaming engine for our tracer capabilities, we initially aimed to leverage all of its key features, from reliability, repeatability, and exactly one guarantees. This included enabling checkpointing with RocksDB on S3 and watermarking to handle the late arriving spans effectively. However, The team learned over time that enabling these features significantly impacted our job's overall stability and backpressure handling. With volumes reaching 200 to 250 million spans per minute, Flink jobs could never catch up with the past event when processing all records from the previous checkpoint, creating a persistent lag that compromised real-time processing. Given this performance constraint, several strategic decisions were made. Checkpointing was disabled entirely, except for the source reader we will discuss later. Save points were never configured, and after experimenting with watermark configurations to handle late arriving spans, watermarking was also disabled. So we also keep all the raw spans in a hot store. This means that we don't need to hold the entire trace in memory while waiting for the late spans. We can just look it up anytime in the later stage from the hot store. However, at this point, incomplete traces are just marked as broken traces, resulting in some lost edges where parent and child spans cannot be referenced. By disabling these features, the team knowingly traded reliability for performance. Since OpenTelemetry tracing already samples only a fraction of total traffic, typically 1 to 5% of requests, losing occasional traces during processing remained acceptable. It is important to note that all these features were disabled only after thorough deliberation. The trace building operator faces a very unique challenge that significantly impacts our resource requirement. Unlike traditional Flink jobs that typically need 32 to 64 GB memory, we require all spans of a trace to be held within one task manager, as the relationship between services are established through parent-child connection. It makes distributed processing per trace really hard. The scale variability we are dealing with is enormous. As Vineet mentioned, traces can range from 10 to 300,000 spans, as our team handles both microservices and monolith processing. A single trace with its complete span hierarchy, along with its metadata, can exceed hundreds of megabytes in size. We simply cannot impose any artificial limits per trace without compromising to troubleshoot production issues. This architectural reality forces us to provision memory at a very higher end, around 176 GB currently, to maintain the critical operational visibility. Now, quickly breaking down the memory allocation, we have to allocate the largest portion to our heap space since we are doing windowing and processing operations on it, which becomes essential for the individual traces. The remaining 35% goes to the off-heap memory, which has been carefully divided on operational needs. Two-thirds of the off-heap is allocated to the managed memory, and here's where things get interesting from checkpointing perspective. Although scheduled checkpointing is disabled for performance reason, the custom S3 source reader still performs a strategic checkpointing during a job shutdown. This ensures proper notifications are sent to delete processed S3 records, maintaining data lifecycle hygiene. Flink is configured with checkpointing to utilize RocksDB, which resides entirely within the managed memory space. RocksDB is notoriously aggressive in its memory consumption. It consistently operates at near 100% optimization utilization for the available managed memory. And the remaining third of the off-heap serves as direct memory, primarily function as network buffers for data shuffling between task manager. Through our optimization efforts in our moving span records entirely across task manager, network memory utilization has been kept well under control at around 60%. Now, despite extensive Flink configurations and infrastructure optimizations, persistent job restart issues continue to plague day-to-day operation. While small data loss blips are acceptable for service dependency and tracing workloads, job downtime lasting minutes or hours is unacceptable. The most persistent issue encountered over the past year involves uncaught exceptions from peer connection resets and task manager fallouts. These failures trigger infinite restart loops where healthy task manager cannot communicate with the failed ones, creating cascading failure patterns. While the network level resolution efforts are undergoing, an immediate operational solution was essential. To address this challenge, a custom Flink Kubernetes operators was designed to auto-remediate failed Flink jobs. The Kubernetes operator deploys a cron that continuously monitors all running Flink jobs for continuous restart patterns by querying the Flink REST APIs directly. When detected, the operator examines the job manager and task manager status and logs through Flink APIs to confirm whether the error stems from remote transport exception. After reaching a configurable threshold through repeated verification checks, the operator issues targeted Kubernetes deletion commands for the job manager pods, forcing a complete reset and restart cycle. In our experience, deleting the job manager ensured bad task managers are phased out while spinning new ones to maintain quorum. Critical safeguard prevent operational chaos. The framework verifies the job manager wasn't recently created, indicating auto remediation is already in process. This capability has dramatically reduced unpredictable production incidents, including late night PagerDuty calls, and ensuring SLA commitments are consistently met. Our observability strategy focus starts with these two critical metrics that reveal system health immediately. We monitor total incoming traces as our primary health indicator, detecting deviations by comparing current ingestion patterns against previous days or weeks. Additionally, we track edges emitted from the service dependency job, where a healthy edge to trace ratio confirms our trace correlation is effectively mapping the service relationship. It provides architectural confidence in our distributed system. We have more panels providing deeper visibility into pipelines filtering logic for handling billions of daily spans. The filtering strategy explained by Vineet intentionally removes 20 to 30% of incoming spans to focus on only meaningful service interaction. Sampling currently shows zero activity as we process full data volumes from upstream through our filtering mechanism. The filtering breakdown, though, reveals targeted data selections around some key areas. The time-based filtering, which excludes outdated entries, removes less than 1% of span. Tag-based filter out approximately 15 to 20% of total volume, where we only retain specific spans, root spans, spans with proper duration, ingress or proxy spans that provides only meaningful insights. While service level filtering applies a regex pattern to just exclude noisy infrastructure services. They are really low, around only 0.1%, but they provide precise control over our service selection. This granular approach enables maintaining high quality dependency map and catching issues before they become downstream, before they impact downstream analysis. Our team uses JMS Exporter to expose Flink metrics to Grafana for monitoring the job health parameters. Checkpoint size and duration patterns panels show negative values because checkpointing is currently disabled. We still keep these panels to ensure the configuration status is in place. Almost every metric that Flink emits available in our dashboards. Focusing on the data source side, we maintain panels for S3 bucket sizes. We need to keep an eye on unprocessed data sitting in these S3 buckets. If any particular buckets grows out of bounds, that's our early sign that did something wrong in our upstream servers. Even if the S3 bucket size start piling up faster than we can process it, we are potentially looking at significantly high back pressure scenarios that can cascade through our entire pipeline. And finally, the following 6 patterns show us exactly where bottlenecks occur and how our operators perform under load. In our job, as of today, the Flink and Mapper operator hits 60 to 90% soft back pressure at different intervals in a day. That's actually expected since this is the heaviest lifting operator, which is responsible for billions of spans. When we look at the busyness pattern though, the operator runs at 80 to 95% capacity at peak times. So the operator is working hard, but still staying within bounds. What's interesting is our edge aggregator operator, which shows high variability of 75% busyness. That's the orange line, which is again expected given the dynamic nature of the edge's creation. Meanwhile, source operator occasionally spike to higher busyness, but generally stays healthy, indicating occasional upstream pressure doesn't cascade through the system. The real win here, though, is what we are not observing. Near zero hard back pressure across all the operators. That's on the right bottom corner. This tells us that the pipeline stays resilient even if the operators are busy. Data keeps flowing instead of completely stalling. All right, summing it all up, looking at the positives first. Flink enabled rapid deployment to serve service dependency mapping at production scale. We partnered with the internal streaming team. With our collective deep expertise, we ended up creating standardized wrappers for hosting solutions like this. Operational effort required minimal intervention with the pre-built integrations for popular infrastructure such as Kafka and Iceberg. There is a sister team utilized Kafka as their persistent layer. The integrations have greatly simplified deployment across various data platforms. Additionally, observability was very easy to configure, provide clear insights to help improve each step of the job. And with Flink's robust open source ecosystem and consistent quality improvements in every release, the team felt confident it for production workloads of this scale and complexity. Despite Flink's initial success, several operational challenges emerged that questioned whether it was the right long-term solutions for our specific use case. The most critical issue involved failed jobs entered into continuing restart phases, sometimes never recovering until manual intervention through job manager termination. This forced us to build the resilience mechanism we discussed earlier, and we have to continuously evolve it. That creates an ongoing maintenance burden for us. We look forward to connect with the open source community deeper to understand how to mitigate these uncaught exceptions fully. From a cost perspective, maintaining large states in memory for trace context building drove significant memory requirements, directly translating to higher cost infrastructure cost. And ironically, the team had to disable checkpointing, one of the Flink's core strengths, because it just wasn't needed, highlighting feature misalignment with actual requirements. These factors combined to create a situation where Flink's enterprise-grade features were solving the problems the team did not have in the first place, while introducing operational complexity that did not align with us. Now, looking ahead, from all the learnings after running Flink streaming jobs, we have been inspired towards building a stateless streaming architecture with ingestion patterns specifically designed per business case, without overhead of hosting general purpose solution. These are ongoing discussions, design discussions, which centered around maintaining ephemeral buffers to hold incoming data streams, and then using event-driven functions to consume these stream chunks for either building complete traces or individual edges. The intention is to create a system that is both lightweight and horizontally scalable. Since this design is still evolving through team discussions and proof of concept, we plan to potentially showcase the final solution in future data events. While we seek a more purpose-built streaming framework for tracing, Flink still remains an integral part of Salesforce data streaming infrastructure. And following are the other three monitoring pillars at Salesforce, which rely on Flink as their streaming engine. Starting with the log processing on the left, Flink handles comprehensive parsing of all microservices and monolith applications. Collectively, the job runs over 1,000 nodes, where operators extract insights and performs very intensive aggregation. For metric streaming, services emit high granularity metrics that flow through Flink pipelines to Druid. Then there is event ingestion at enormous scale, billions of events daily, matching trace volumes in complexity. Each of these observability tools demands zero data loss and complete repeatability. Every single data point plays a very important role in operational diagnostics and incident resolution, making Flink's reliability guarantees essential. We also look forward to present a highly dynamic general-purpose Salesforce streaming platform at a future data streaming event. And before opening up for comments and questions, we encourage the attendees here and the community to check out Salesforce engineering blog for topics included but not limited to building in-house Kubernetes platform, to cost reduction techniques on cloud, and much more. With that, thank you so much for your time today. Feel free to reach out to either of us if you'd like to continue the conversation, and we hope you enjoy the rest of the conference and have a great week. Thank you. Yes. Yes.
Can you share more details about the parallelism which you managed within the pipeline? Like, is that a reasoning why you took the decision to, because the data is like embedded with nested events, or is there any other reason why you have to?
Sure. Okay.
Does that not have any network movement because you are actually changing the partitioning?
That's a great point. So the question is, why do we have to change our parallelism so much, right? Even though the spans are all coming to the same partitions, and we have to just process it through. Ultimately, when we were, okay, let me get there very quickly. Okay, awesome. So ultimately, what really happened in that 4 stages, you can see there are around 7 operators We divided them into 4 stages. The first stage is to just read from the source. Second is the trace build. Third is edge building. And the fourth is aggregations. We concluded in that manner. While we are doing filtering, record mapping, there are a bunch of more operators which we have kind of like chained together. While we were testing it out, we realized generating metadata and attaching to an each edge was really adding a lot of size, a lot of kilobyte size to each data point, which is not in conjunction with a raw data span coming in. So we conducted a very thorough, this is almost a 6 to 9 months operation where we tried to really get to a number where all of these operators work well, they keep busy, but don't go into back pressure. We wanted to really squeeze out our resources, and that's how we got to this number. The reason being the last parallelism is 1400, and while this 2000, we can keep this as it's the same as it actually. But while we were doing it, we were eventually running out of memory. For that, those edge aggregations and the metadata attached with them. So we ultimately have to relax the parallelism so that each task slot gets a bit more memory than required. Yeah, that was too minimal for us. So we already allocated around 12 GB to network buffers each task manager to begin with. While we did all these optimizations and when we changed this parallelism, the effects were really, really low.
One question to close. Do you have any deduplication use case in this?
Deduplication use case. Okay, that's a great point. At this point in time, we don't. We consider the trace spans as a time series data, right? We exactly receive once. That is something which the collectors at our upstream servers have taken care of. So we are guaranteed to receive a single event only once. And we kind of skip traces or skip data events which possess some kind of exception and an error instead of trying to reprocess it again. We can afford to lose some data, but eventually I think we get to a stage where we have to think about this too. Yeah.
You are doing a lot of simulation, deceleration through this chapter. Did you adopt to any formats like protocol?
We are strictly on Avro serialization. That's been adopted from the day one. We never fall back to Cairo or any other. We kind of like experimented with both protobuf and Avro, but collectively, since this entire streaming infrastructure is a Salesforce wide offering, so the Avro was adopted as the standardized serialization deceleration. And being very honest, Avro works great. We did not see much performance boost with protobuf. We experimented with that, but it was merely 5%, which was not, for us, it was not really beneficial to maintain it in the future too. Yeah. Yeah.
Service-to-service dependency that you are trying to evaluate, how come you have to process 300K spans?
Sure. Awesome, great question. So service-to-service dependency is derived from parent span to child span, right? Every span has a parent ID and its own ID. To build this entire service-to-service dependency, each trace has to be taken out. The relationships between service A to service B has to be defined, and then a new edge key needs to be generated from that. So we have to process all the spans as possible, and we have no control over the volume. That's the first thing. So at this point, with 300 billion, it can be more later. Does that answer your question?
Kind of. And
Trace propagation instead of using this hierarchy based. Can you suggest the services to kind of make data tracing a bit better for you to process easily? Is that a solution?
Okay, I think I get your question. Do you want to answer this?
yeah, that helps a bit, but we get like spans and traces from more than 100 services, and it gets a bit challenging to like improve the instrumentation for each service. Coming to the trace reconstruction again, we need a transactional view of the service dependency, not just service dependency. So that helps us. Once we reconstruct the trace, we add some attributes so that we can connect the whole user journey request.
We are trying to do the other in that mode, but we are expanding the trace across the services as much as the request can flow. We are not limiting upstream. This is purely generation of the service dependency. What we could do, and some optimizations are done, we just need the entry point, which is the ingress spans, and everything in the middle can be dropped,
Yep.
which is what the initial processing does. And you're looking at the
Just to follow up on that, so we follow the standard open telemetry trace format. So building that custom format is, at this point in time, is not in place since we use Zipkins, which is the standard format for the trace. If we go custom, obviously, that can be, we can improve on that. Yeah. Any question there? Yes.
I have a question about the JVM tuning since you have a very large heap size. What JVM version and what type of GC do you use?
Okay, awesome. We are on Java 17 and G1 GC strictly. So, and that has been, I think, standard from Flink 1.14, if I am correct. We have not seen too much GC activity after we have provided this enormous 100 GB of heap for each task manager. So even though the GC happens, it is not stalling the operators or any back pressure we have seen. Does that answer your question?
Yeah.
Yep. Okay.
Well, one additional question: Have you tested, let's say, on Java 21 and
Not yet.
GC and
Not yet. Not yet. We so the streaming team within the Salesforce upgrades the Flink version, and we follow the same pattern with them. So as we new stable versions comes out, we eventually go up and up. But yeah, I think that is in the works this year actually.
What led you to disable watermarks completely? Did you have any windowing-based aggregations?
No, so we had watermarking just to wait for the late arriving spans. What does it mean? So we build a 3-minute context window where we assume all the spans for a trace will come within these 3 minutes. And that's not actually in real time. A span or a service call can happen after 10 minutes or 20 minutes. So we had watermarking just to wait for the late arriving span. If another span comes, we wait for some more time for the next late arriving span. And that just created kind of like a situation where a lot of data was kept in the process itself and not, the watermark was not flushed out. So ultimately, we just decided to just disable it entirely. Just not wait for it and ultimately mark the edges as not there at all. We mark them as broken traces. We are working through a solution where we will be able to build that missing context too, but at this point in time, we have disabled it.
So you don't have the 3-minute.
We have a 3-minute, we just wait for 3 minutes, whatever spans we receive for a trace, we build edges from that and moves on.
Based on processing time.
Exactly. Okay. All right, thank you so much. There were some great questions. Appreciate this. Thank you.